Hello everyone, welcome to the very first video of our new series Data Structures and Algorithms in Python. My name is Samuel and I am thrilled to have you here. This series is all about helping you master the fundamentals of data structures and algorithms, or DSA as we often call them. Now, why is mastering DSA important? It's not just about solving coding problems, it's about learning how to think like a programmer and designing solutions that are both efficient and scalable. These skills are highly sought after in job interviews, essential for tackling real-world challenges, and incredibly useful for writing optimized code. So without further ado, let's dive in and lay the foundation for this exciting journey. Let's begin by answering the big question. What are data structures and algorithms? So data structures are the way we store and organize data so that it can be accessed and modified efficiently. Think of them as tools or containers, each with its own purpose. For example, imagine storing books in a library. You could stack them on a table, place them in a single row, or organize them on shelves by category. Each approach is a different type of data structures. Algorithms, on other hand, are step-by-step instruction or procedures for solving a problem. Let's go back to our library example. If someone wants a book, how do you find it? You could check each book one by one, or you could search by category, or even by the author's name alphabetically. These are different algorithms applied to the same data structures. So let's take a closer look at data structures. They come in many forms, but the goal is always the same: organize data in a way that suits the specific task at hand. For instance, if you need to access items in a specified order, a queue might be the best choice. If you need to retrieve an item quickly using a unique identifier, a hash table would work better. Understanding the right data structure to use in a given situation is one of the key skills of a good programmer. For example, if you are working with a to-do list, you might use an array. But if you need to keep track of a game's high scores in real time, you might opt for a heap or a priority queue. We will explore all this in detail throughout the series. Now let's turn to algorithms. Algorithms are step-by-step instruction we use to manipulate data. They help us solve problems like sorting a list, searching for an element, or finding the shortest path between 2 points. But algorithms aren't just about solving problems. They are about solving them efficiently. For instance, imagine you need to sort a deck of cards. You could shuffle through them one by one, or you could use a more systematic approach like dividing the deck into smaller piles or sorting those first. This is the essence of what algorithms do. They provide the logic behind efficient problem solving. Now, why are DSA important? The answer lies in its application. First, DSA is a key focus in job interviews. Recruiters often test your understanding of data structures and algorithms because it shows how well you can solve problems under pressure. Second, DSA plays a critical role in real-world application. Think of tech giants like Google or Amazon. They use complex algorithms to make their services faster and smarter. Finally, DSA helps optimize your code, making it faster and more efficient. For example, the difference between a good algorithm and a great algorithm can mean saving hours of processing time on large data set. Now let's look at some real-life examples of how DSA impacts our everyday lives. Search engines like Google rely heavily on algorithms to fetch the most relevant results in milliseconds. Social media platforms like Instagram and Facebook use algorithms to determine what content appears in your feed. When you shop online, algorithms analyze your browsing history to recommend products you might like. And when you use GPS navigation, algorithms calculate the fastest route to your destination. These real-world applications are proof of how integral DSA is to modern technology. There are two main types of data structures: linear and non-linear. Linear data structures include array, linked list, stacks, and queue. In this, data is stored sequentially, making it easy to traverse one element after another. For instance, An array is like a row of lockers where each locker holds one item and can be accessed by its number. Non-linear data structures like trees and graphs are more complex. They allow us to represent hierarchical or interconnected data. A family tree is a perfect example of a hierarchical data structure, while a network of connected devices can be represented as a graph. We will cover these types in detail in upcoming videos. So before we wrap up, let's touch upon an essential concept: time and space complexity. Time complexity measures how the runtime of an algorithm changes with the size of the input. Space complexity, on the other hand, measures how much memory an algorithm uses. These metrics help us evaluate the efficiency of algorithms. For example, sorting a list of 10 items might take a fraction of a second, but what if the list had a million items? The time complexity tells us how the algorithm will scale, and this is something we will explore further in the next video. In our last video, we laid the foundation for data structures and algorithms. Today, we are taking it a step further by diving into one of the most critical concepts in DSA, which is time and space complexity and how to analyze them using big O notation. If you have ever wondered how to evaluate the performance of your code or choose the most efficient algorithm for a problem, this video is for you. Let's get started. So what is big O notation? Big O notation is a mathematical way to describe the performance of an algorithm. It gives us an estimate of how the time or space requirements of an algorithm grows as the size of the input increases. For example, imagine you are trying to find a specific book in a library. If the books are randomly arranged, you might need to check every single book. This is an example of order of n, where the time required grows linearly with the number of books. On the other hand, if the books are sorted alphabetically, you can use a more efficient approach like binary search, which allows you to find the book much faster. This is order of log n, where the time grows logarithmically as the library size increases. Big O focuses on the worst case scenario, the maximum time or space an algorithm might take, so you are prepared for the most demanding situations. Now let's talk about time complexity. Time complexity measures how the execution time of an algorithm changes as the size of the input grows. It helps us predict whether an algorithm will perform well as our data grows larger. Let's look at a few common time complexities. Order of 1. This means the algorithm's runtime doesn't depend on the input size. For example, accessing an element in an array using its index is order of 1. Next is order of n. Here, the runtime grows linearly with the input size. Imagine you are searching for an item in an unsorted list. You might have to check each element one by one. Next is order of n square. This represents quadratic time complexity, where the runtime increases exponentially with the input size. A common example is nested loops, like checking every pair of elements in an array. Let's break down order of n square with a quick example. Suppose you are trying to find duplicate elements in a list. A simple algorithm might compare every element with every other element in the list. As the input size grows, the number of comparisons grow quadratically. Next, let's explore space complexity. Space complexity refers to the amount of memory an algorithm uses as the input size grows. This includes like the memory required to store the input and additional memory used during the execution like variables, arrays or stacks. For example, if an algorithm creates a copy of the input array, the space complexity will be order of n because the space required increases linearly with the input size. Understanding space complexity is crucial, especially in environments where memory is limited like embedded systems or mobile devices. Let's review some of the most common big O notations and their meanings. Order of 1, which is constant time. The operations time remains the same regardless of input size. Example, accessing an element in an array by index. Next is order of log n, logarithmic time. The runtime increases slowly as the input size grows. Example, binary search in a sorted list. Next is order of n, which is linear time. The runtime increases proportionally with the input size. Example, iterating through an array. Next is order of n square, which is quadratic time. The runtime increases quadratically as the input size grows. Example, nested loop for pair comparisons. Next is order of 2 raised to n, exponential time. Runtime doubles with each additional input. Example, solving the Tower of Hanoi problem recursively. So to better understand these concepts, let's look at some real world examples. So checking if a number is even or odd using the modulo operator is order of 1, where searching for a contact in an unsorted phone book is order of n. Finding a word in a dictionary using a binary search approach is order of log n, where comparing every student in a class to find who has the same birthday is order of n square. So this is a simple example of space complexity. Just read it. Now let's discuss the time versus space trade-off. In some cases, you can reduce the time complexity of an algorithm by using more memory. For example, calculating the n Fibonacci number recursively takes order of 2 raised to n time because it recalculates values multiple times. By storing intermediate results in an array using dynamic programming, the time complexity is reduced to order of n, but the space complexity increases to order of n because of the additional memory used. Today we are diving into one of the most powerful and versatile data structures in Python, the list. If you have ever wondered how to manage and manipulate collections of data efficiently, this video is exactly what you need. We will cover everything you need to know about Python list, from the basics to advanced operations. You will learn about syntax, indexing, slicing, nested list, and even powerful techniques like list comprehensions. We will also explore the common methods you will use daily when working with list. By the end of this video, you will have a solid grasp of list and the confidence to use them effectively in your projects. So what exactly is a Python list? Imagine a container that can hold a sequence of items. These items can be numbers, strings, booleans, or even other lists. A list is ordered, meaning the elements are stored in a specific sequence. It's also mutable, which means you can modify it after creation. So here's an example. This list contains a mix of integers, strings, floating point numbers, and a nested list. Python lists are incredibly flexible, which is why they are used so widely in programming. The syntax for creating a list is simple. Use square brackets and separate each element with a comma. Let's see some example. So the first one is empty list. This is the list of integers which named numbers. Then the last one is a mixed data types, where integer is present, string is present, and a boolean value is present. As you can see, list can hold a variety of data types, making them ideal for dynamic and versatile data handling. Now let's talk about indexing. Every element in a Python list has a unique position called an index. The index starts at 0 for the first element. You can also use negative indexing to access element from the end of the list. So here we can see a list named fruits, which contains the elements apple, banana, and cherry. So we access with positive index first. So fruits of 0, like the index will be like 0, 1, and 2. So fruits of 0 will print the output apple, and the fruits of -1, which is negative indexing, will print cherry, since the negative indexing will access the element from the end of the list. So this feature is extremely useful when working with specific elements in a list. Slicing is like cutting a cake. It lets you extract a portion of the list. So we can use the syntax as list start colon end colon step. Here's how it's work. First we initialize a list of integers numbers, then we slice with start and end. So 1 to 4 means the element from 1 up to 3 will be printing. Like the index will be like 0, 1, 2, 3, 4 and 5. So 1, 2, 3 will be printing. Slicing is an elegant way to manipulate parts of your data without altering the original list. Python list come with built-in methods to make your life easier. Let's explore some. So these are some of the common Python list methods we use. So first one is append, which add an element to the end of the list. The second is extend, which add multiple elements to the list. The insert method is used to add an element at a specific position. Remove method is used to remove the first occurrence of a value. Pop will remove and return an element. The sort will sort the list. So let's see examples of each of these. First, append adds a single element to the end of the list. Here the list is 1, 2, 3, and when we use the append function like numbers, the array, the list dot append 4, which will result in a output like this 1, 2, 3 and 4. The extend function will add multiple elements to the end of the list. Like this is a list of 5, 6, which add both the 5 and 6 to the list. So the output will be like 1, 2, 3, 4. Then it will print 5 and 6. And next is remove, which deletes a specific element. So here the list is apple, banana and cherry. We will remove banana so that the output should look like apple and cherry. This is the output of it. The next one is pop method, which will pop the element in the specified index. For example, here we pop the element at the index 0, which is apple. So it will pop the element and the output should only contain cherry in it. So next method is sort, which sorts the list. For example, here the list is unsorted. So we will sort the list using the sort method. So the output should be sorted like 1, 2, 3 and 4. The next is reverse method, which will reverse the list. So if the element is 1, 2, 3, 4, it will reverse, like print backwards, like 4, 3, 2 and 1. So next is iterating through a list. To work with list, you will often need to iterate through them. So here's an example of a simple iteration. So the list is apple, banana and cherry. So for fruits in fruits, which means the elements in this list will print fruits, which is each element will be printed. So output should be like apple, banana and cherry. So we can also use the enumerate keyword to get both the index and the value. So by using the enumerate, we can get both the index and the value. Next is list comprehension. It is a concise way to create list. So this code here represents to create a list of squares. The first example calculates square of numbers from 0 to 4. The second example includes only numbers divisible by 2. Nested lists are lists within list. They are often used to represent matrices or grids. So here is an example. Here matrix of 0, 1 access the second element of the first list, which is 2. Nested lists are powerful for organizing complex data.
If you are learning programming or preparing for interviews, understanding arrays is a must. Arrays are one of the most fundamental data structures. They let you store and manipulate collections of data efficiently, and they are the basis for many advanced algorithms. Think of an array as a collection of lockers where each locker can store one item, and every locker has a unique number called an index. In Python, we use list as a substitute for arrays. They are incredibly versatile and also allow us to perform operations like reversing, finding the largest and smallest elements, and summing up values. Today, we will solve 3 common array problems step by step, ensuring you understand the question and solution for each. By the end of the video, you will have a solid foundation to tackle array challenges confidently. Before we dive into the problems, let's quickly define what arrays are. Arrays are used to store multiple values in a single variable, which makes them ideal for handling datasets or collections of numbers, strings, or objects. In Python, we use list to represent arrays. So here's an example for array which contains the element 10, 20, 30, 40, and 50, which have the indices of 0, 1, 2, 3, 4 respectively. Each value in the array is assigned an index starting from 0. This index helps us access or manipulate specific elements in the array. Now that we understand the basics, let's move on to our first problem. The first problem is to reverse the element of an array. For example, if the input is a list containing 1, 2, 3, 4, and 5, the output should be a list containing 5, 4, 3, 2, 1, which is the reversed form of the input. So the goal is to rearrange the array so that the first element becomes the last, the second becomes the second last, and so on. This operation is widely used in algorithms, especially when processing data in reverse order. So Python makes reversing an array super simple by slicing. That's the first solution. Here, this is a slice operation that tells Python to start at the end of the list and move backward to the beginning. This method is very efficient and requires only one line of code. The second solution is by using a loop method. If you want to understand the logic behind reversing, you can use a loop. In this approach, we iterate from the last index to the first and construct a new array by adding each element to it. While this method is slightly longer, it's a great way to understand how reversing works. The second problem is to find the largest and smallest numbers in an array. For example, if the input is 31, 41, and 59, then the maximum element present in that input is 9. So we need to print 9. Then the minimum element present is 1. So we need to print 1. This problem is crucial when analyzing data, such as finding the highest score in a game or the smallest expense in a budget. The first solution is by using the built-in function. Python provides built-in functions to solve this easily. The max function returns the largest element, while the min returns the smallest. These functions are efficient and very easy to use. The second is the manual approach. For situations like coding interviews, a manual approach demonstrates your understanding of the logic. Here we initialize the maximum and minimum values with the first element of the array and then compare each element to update this value as needed. Our third problem is to calculate the total sum of all elements in an array. For example, if the input is 10, 20, and 30, the output should be 60, since the sum of 10, 20, and 30 is 60. This is useful when you need to compute totals like summing up expenses or calculating the overall score of a game. The first solution is by using the sum function. The easiest method is to use Python's built-in sum function. This function iterates through the array and returns the total sum of its elements. Second one is iterative approach. If you would like to implement this manually, you can use a for loop. Here we initialize a variable total to 0 and add each element of the array to it. This approach helps to understand how summing works internally. Now let's combine everything we have learned and apply. So here we initialized an array with 10, 20, 30, 40, and 50. We will print the original array. So the original array will be this. Then we print the reversed array. The reversed array will be reversed array of this original array. Then we print the maximum value 15 and minimum value 10. Then we will finally print the sum as 150, since the sum of this array is 150. The two-pointer technique is a strategy where we use two indices or pointers to traverse a data structure. This technique is particularly helpful when working with arrays or linked lists. The idea is to move these pointers to solve problems more efficiently than traditional approaches. But why is this important? By using two pointers, we can often reduce the time complexity of problems that would otherwise take quadratic time. Instead of using nested loops, you can solve these problems in linear time, making it a favorite among programmers. There are two main types of two-pointer techniques, each suited for different types of problems. First one is opposite direction. This is where two pointers start at opposite end of the array and move towards each other. It's commonly used for problems involving pairs of finding specific sums, such as the classic two-sum problem in sorted arrays. The second one is same direction. Here both pointers start from the same end and move in the same direction. This approach is typically applied to sliding window problems like finding the longest substring without repeating characters or the maximum sum of a subarray. Now let's look at some of the common use cases of two-pointer techniques. Finding pairs with a specific sum. For example, in a sorted array, you can use 2 pointers to efficiently find two numbers that add up to a target. Next one is the removing duplicates. This is a common problem in sorted arrays where you need to remove duplicates in places. Next is partitioning arrays. For instance, separating even and odd numbers within an array. Next is sliding window problems. This includes problems like finding the longest substring without repeating characters or finding the smallest subarray with a given sum. And next is merging two sorted arrays, a common task in merge sort and other sorting related algorithms. So here are a few example problems you can solve using the two-pointer technique. First one is pair sum problem. Find if there are two numbers in a sorted array that add up to a given target. The second one is remove duplicates from sorted array, that removes all duplicate in place and return the new length of the array. The third one is longest substring without repeating characters. Find the longest substring in a string that doesn't contain any repeated characters. Now let's take one of these examples and solve it step by step. The problem is find two numbers in a sorted array that add up to a given target. This is a classic use case for the two-pointer technique and it demonstrates how efficient this method can be. The approach is simple. Start with 2 pointers, one at the beginning of the array, which is left pointer, and the other at the other end, so which is right pointer. So calculate the sum of the element at these pointers. Then we compare the sum with target. If the sum equals the target, you have found the pair. If the sum is less than the target, move the left pointer one step forward to increase the sum. If the sum is greater than the target, move the right pointer one step backward to decrease the sum. Repeat this process until the pointers meet or the target is found. So here's a Python implementation of the approach. The code runs in order of n time and is much more efficient than using nested loop, which would take order of n square. For the other problems we discussed earlier, like removing duplicates or finding the longest substring without repeating characters, I have already uploaded separate videos. Be sure to check those out for more in-depth explanation and coding examples. Why should you use the two-pointer technique? It saves time by reducing the complexity of many problems from quadratic to linear. It simplifies the logic, especially for problems on sorted data structures. It's widely applicable, making it a must-know for coding interviews and competitive programming. However, like any technique, the two-pointer method has its limitations. It often requires the input to be sorted, which could add overhead if sorting isn't already done. It's not suitable for problems that involve unsorted or multi-dimensional data without pre-processing. Handling edge cases such as empty array or arrays with duplicates can add complexity. The two-pointer technique is not just theoretical. It's used in real-world applications like solving advanced problems such as threesome and foursome, implementing sliding window algorithms for network traffic analysis or DNA sequence matching, merging sorted arrays efficiently in sorting algorithms like merge sort. Here are some tips to master the two-pointer techniques. Always ensure the array is sorted or sort it beforehand if necessary. Visualize the movement of pointers to understand how the solution evolves. Test your solution against edge cases like empty arrays, arrays with duplicates, or arrays with negative numbers. Practice on platforms like LeetCode or HackerRank to strengthen your skills. Stacks are basic but super powerful data structure that you will see everywhere, from coding interviews to real-world applications. We will break down stacks, show you how they work, and give you clear examples of how to use them. By the end of this video, you will understand how stacks work and be ready for our next video where we will tackle stack problems in Python. First thing first, what exactly is a stack? Simply put, a stack is a data structure that follows the rule of LIFO, which means last in, first out. Imagine you have a stack of plates or books. When you put new plates on the stack, they go on top. To remove one, you take the top one first, not the ones at the bottom. That's exactly how stacks work in programming. Simple, right? Let's take a look at the main features of stack. First is, as we said earlier, LIFO, which means the last item you add is the first one to be removed. Next one is limited access. You can only access the item at the top, not the ones underneath. Next is dynamic or fixed size. Depending on how you use it, a stack can grow or shrink in size. These features make stacks really useful for certain tasks. Stacks have some key operations that help us work with them. Here are the most important ones. First one is push. Add an element to the top of the stack. The second one is pop method, which remove the top item. Next one is peek, where we look at the top item without removing it. Next is empty. Check if the stack is empty. The next one is size. Find out how many items are in the stack. Once you know this, you are ready to start using stacks in your code. Let's start with the push operation. This is when we add a new item to the top of the stack. For example, if the stack contains an element like 10, 20, 30, and if we push 40 to it, the new stack will contain 10, 20, 30, and 40. So now 40 is at the top. So when we perform the pop operation, 40 will be the first to come off. Next, the pop operation. This is when we remove the top item from the stack. For example, if we have stack like this 10, 20 and 30, if we pop, we remove 30. So the stack becomes 10, 20. Keep in mind, if you try to pop from an empty stack, you will get an error. This is called stack underflow. The peek operation let us check the top item without removing it. For example, if the stack contains 10, 20 and 30, by using the peek operation, it will return 30, but the stack stays the same. It's useful when you want to see what's on top without changing the stack. Next is empty operation. This checks if the stack is empty. So it will return true if the stack has no elements, otherwise it will return false. For example, if the stack contains elements such as 10, 20 and 30, it is not empty, so it will return false. And if a stack containing no elements and if we use is empty, it will return true since the stack is empty. So you might be wondering, where do we use stacks in real life? Well, here are some examples. Function calls. When a function calls another function, it's like stacking them up in a certain order. Undo or redo. Ever used undo in a text editor? It uses stack to remember your actions. Expression evaluation. Stacks helps in evaluating expression like math problems. Backtracking. In games and puzzles, stacks are used to remember past steps. So stacks are used all over the place. So this is the example for push and pop. We start the stack at empty. So when we push 10, the stack will become 10. When we push 20, the stack will become 10 and 20. And when we pop the element at the last, the 20 will be removed and the stack will contain 10. So if the stack contains elements such as 10, 20 and 30, by using the peek method, we can get the top element, which is 30. So now let's see how to work with stacks. So Python makes it easy to implement stacks with list. Here's how. First we initialize the stack of empty list. Then we append 10 to it, which means we will push 10 to the stack. Then we append 20, which will push 20 to the stack. In pop operation, using the pop method, we can pop the top element from the stack. For example, since in the previous example, we appended 10 and 20 to the stack, when we pop, the top element, which is 20, will be popped from the stack. Stacks are amazing, but like everything, they have their pros and cons. So some advantages are it is easy to implement. Fast operations like adding or removing items is quick. Great for memory management. So Some disadvantages are you can only access the top item. In today's video, we will be diving into some interesting stack problems in Python. If you are new to stacks, don't worry, we will go over what stacks are, how they work, and tackle two important problems that can be solved using stacks, which are balanced parentheses and reversing a string. By the end of this video, you will have an understanding of how stacks work and how to apply them to solve real-world problems. Let's begin by quickly reviewing what a stack is and how it operates. A stack is a linear data structure that follows the LIFO, which is last in first out principle. This means that the last element added to the stack is the first one to be removed. Think of a stack as a pile of books. The last book you put on top is the first one you will take off. The two main operations that a stack supports are push operation, adding an element to the top of the stack, then pop operation, removing the element from the top of the stack. Stacks are widely used in scenarios where you need to reverse things or manage a nested structure, such as parentheses in programming or undo operations in text editors. Let's start with our first problem, balanced parentheses. The problem is simple. Given a string containing characters like parentheses, braces, and brackets, we need to check if every opening parenthesis has a corresponding closing parenthesis and if they are in correct order. To solve this, we will use a stack. The idea is to traverse the string character by character. Then if the character is an opening bracket, then we push it onto the stack. And if the character is a closing bracket, we check if the top of the stack matches the corresponding opening bracket. And if it does, we pop the stack. Otherwise, we return false. At the end, if the stack is empty, the parentheses are balanced. If there are still unmatched opening brackets in the stack, the string is not balanced. Here's the Python code to implement this solution. So let's break it down. First, we create an empty stack to keep track of the opening brackets. So as we loop through the string, if we encounter an opening bracket like this, then we push, which means we will append it to the stack. Then if we encounter a closing bracket, we check if the stack is empty. And if it's not empty, we pop the stack and check if the top element matches the corresponding opening bracket. So we check if the stack is empty, and if it's not empty, we pop the stack and check if the top element matches the corresponding opening bracket. And if it doesn't match, we return false. After processing the string, we check if the stack is empty. If it is, all parentheses are properly matched and we return true. If not, there are unmatched opening brackets, so we return false. Now let's move on to another problem, which is reversing a string using a stack. The idea here is to reverse the order of characters in a given string using a stack. Here's how we can do that. First, we push each character of the string onto the stack. Then we pop each character from the stack and append it to the result string. Since stacks follow the LIFO principle, the order of characters will be reversed by the time we pop all of them. Let me show you the Python code to implement this. Here's how this works. We convert the string S into a stack by turning it into a list. Each character in the string is now an element in the list. We initialized an empty string, reversed str to hold the reversed string. Then we enter a while loop that continues as long as the stack has elements. Inside the loop, we pop the top element of the stack, which gives us the last character that was added. Then we append this character to the reverse string. That's the operation being done here. Then we finally return the reverse string, which is constructed by the characters popped off the stack in reversed order. So finally, we return the reversed string, which is constructed by the characters popped off the stack in reverse order. So why do we use stacks for these types of problems? Well, the stack's LIFO nature makes it the perfect fit for problems that require us to reverse elements or match pairs in a specific order, such as parenthesis matching. It ensures that we always deal with the most recently added element first, making it ideal for tasks like parsing expression with nested structures, reversing strings or arrays, undo operations in applications. In today's video, first we will understand what a queue is, then we will explore the basic operations like enqueue and dequeue, then we will learn about different types of queues. After that, we will dive into real-world application of queues. Finally, we will implement queues in Python. By the end of this video, you will have a strong understanding of queues and their practical uses. Let's begin with the basics. What exactly is a queue? A queue is a linear data structure that follows the first in, first out principle. This means that the first element added to the queue is the first one to be removed. Think of it like standing in a line for a movie ticket. The person who joins the line first gets served first. A queue has two main points: the front, where elements are removed, the rear, where elements are added. This structure is widely used in programming for tasks that need to maintain order. Now let's connect this to real life. Queues are everywhere. For example, the line at a ticket counter, printer jobs waiting to be processed, handling calls in a customer service center. Even YouTube processes video in a queue to upload and display them. These real world examples help you understand how queues are applied in programming. Now, let's talk about the operations you can perform on a queue. Enqueue operation, adding an element to the rear of the queue. Dequeue operation, removing an element from the front of the queue. Peek operation, viewing the element at the front without removing it. Is empty operation, checking if the queue is empty. These operations are simple yet powerful, enabling queues to function efficiently in various scenarios. Let's start with the enqueue operation. It simply adds an element to the rear of the queue. Imagine you are adding another person to the end of the ticket line. For example, if we have a queue 1, 2, 3 and we add 4, the queue becomes 1, 2, 3 and 4. In Python, you can perform this operation using the append method on a list. Next is the dequeue operation. This removes the element from the front of the queue. It's like the first person in the line getting their ticket and leaving. For example, if the queue is 1, 2, 3 and 4 and we remove the first element, it becomes 2, 3 and 4. In Python, we can use pop of 0 method to achieve this. Queues come in different types, each suited for specific task. First one is simple queue, the basic FIFO structure. Second one is circular queue. The last position connects back to the first, useful for optimizing memory. Third one is priority queue. Elements are processed based on priority, not just order. Fourth one is DQ, a double-ended queue that allows additions and removals from both ends. Understanding these types helps you choose the right queue for the job. In a circular queue, the last position is connected to the first. This design prevents wasted memory by reusing empty spaces at the front. It's like a conveyor belt that loops around. Circular queues are commonly used in buffering and task scheduling. A priority queue processes elements based on their priority rather than order. For instance, in a hospital, patients with critical conditions are treated before others. Priority queues are widely used in algorithms and real world applications like job scheduling. Queues are extremely versatile. Here are a few use cases. First one is task scheduling. In operating systems, queues manage processes efficiently. Second one is request handling. Web servers use queues to handle multiple client requests. Third one is graph traversal. Algorithms like BFS rely on queues. Fourth one is messaging apps. Background processing often uses queues to manage messages. This example shows why queues are essential in programming. Let's now see how to implement queues in Python using list. the simplest approach but not the most efficient for large queues. Using collections.dq provides optimized operation for queues. Using queue.q, ideal for multi-threading and advanced scenarios. We will use examples to demonstrate each approach. Here's how we can implement a queue using Python's list. First we initialize an empty list, then we append 1 to it, then we append 2 to it, and at the time the queue will contain 1 and 2. Then when we pop 0, which means the element at the index 0 will be popped and 1 will be popped. So the queue will contain 2. And finally, when we print q, it will print 2. This code shows how to enqueue and dequeue elements. In today's video, we will be solving real-world queue problems in Python. We will start by understanding and implementing a circular queue, followed by simulating a waiting line, just like how queue work in real life. By the end of this video, you will have a solid understanding of queue operations and will be able to apply them in real-world applications. So let's get started. Imagine you are at a theme park waiting in a line for a roller coaster. The first person who joins the queue gets to ride first, and the last person waits their turn. This is exactly how queue work in programming. Queues are used everywhere, from customer service systems, scheduling algorithms, and even buffering videos on YouTube. So let's see how we can implement and use queues efficiently in Python. So in this video, we will cover what a circular queue is and why is it useful, how to implement a circular queue in Python, and we simulate a real-world waiting line using queues. Let's start with the first topic, circular queues. A circular queue is a special type of queue where the last position is connected to the first. Instead of leaving empty spaces, when elements are removed, we reuse the space, making it much more efficient. Circular queues are widely used in CPU scheduling, memory management, and buffering systems like music players or printers. Let's look at how a circular queue works. A circular queue supports 4 main operations. First one is enqueue operation, add an element to the queue. Dequeue operation, removes an element from the queue. Peek operation, view the front element without removing it. Is empty or is full. Check if the queue is empty or full. Now let's implement a circular queue in Python step by step. This is how we can implement circular queue by using the enqueue, dequeue, and display functions. This is the Python code to create a circular queue. This function will initialize a queue with a fixed size, and this function will add elements while handling circular indexing. This function removes element and updates pointers, and display function prints the queue element in order. Let's see how our circular queue works. So using the enqueue function, we can add elements while handling circular behavior. Using the dequeue operation, we can remove elements and update pointers. And the display function prints queue element in order. We can test our code by adding the element to the circular queue by using the enqueue operation. And by using the dequeue operation, we can remove elements and check the behavior. And by using the display function, we can display the list. Waiting lines are real-world examples of queues. Think of a bank queue, customer support system, or fast food counter. Everyone gets served in FIFA order. Let's simulate a basic waiting line using Python. This is the code implementation of waiting line in Python. I have already explained it in previous videos, so check that before continuing to the next part. In this code, we use Python's queue to manage a waiting line. People are added to the queue one by one. Then we process each person one by one, simulating a real-world scenario. Let's see the expected output. This is the expected output, and that's how a waiting line works using queues. Today, we are going to learn about linked list and important data structure used in programming. By the end of the session, you will understand what a linked list is, how it stores data using nodes and pointers, different types of linked list, how to implement linked list in Python, advantages, disadvantages, and real-world applications. So let's get started. Before we get into coding, let's first understand what a linked list is. A linked list is a data structure where elements called nodes are linked together using pointers. In an array, data is stored in a contiguous block of memory. This means every element is placed right next to the previous one. But in a linked list, each element or node is stored separately in memory and connected to the next node using a pointer. Think of it like a chain where each link is connected to the next one. Now, let's understand the basic building block of a linked list, the node. Each node has two parts. The data stores the actual value like a number or word. Pointer stores the address of the next node in the sequence. The last node points to null, meaning there are no more nodes after it. There are three main types of linked list, each with different behaviors. First one is singly linked list. Each node points only to the next node in the sequence. Second one is doubly linked list. Each node contains two pointers, one pointing to the next node and another pointing to the previous node. The third one is circular linked list. The last node does not point to null. Instead, it connects back to the first node, forming a loop. Each type has its own use cases, which we will see later. Now, let's look at a simple Python implementation of a node. This code creates a node class where self.data stores the actual value. Self.next is a pointer to the next node, which is none by default. Now that we have a node, let's create the linked list class to manage these nodes. Here, self.head is the starting point of the linked list. Initially, it's empty, meaning the list has no elements. Now, let's write a function to insert a new node at the beginning of the list. The first step is to create a node. Second step is to point the node to the existing head. And the third step is to update head to the new node. New elements are always added at the front. To view the elements in our linked list, we need a display function. This function goes node by node, printing their values until it reaches null. Advantages of linked list: efficient insertion and deletions. Unlike arrays, you don't need to shift elements. Dynamic memory allocation. You can add as many elements as needed. No fixed size. Unlike arrays, linked list can grow or shrink dynamically. Some disadvantages are more memory usage. Each node needs extra space for a pointer. Slower access time. You must traverse the list to find an element, unlike arrays where indexing is order of 1. This is why linked lists are preferred for scenarios where insertions and deletions are frequent. Now, where are linked lists used in real life? Some common applications include memory management, where dynamic allocation of memory, undo or redo features used in text editors like MS Word, graph representation, adjacency lists use linked list, scheduling algorithms used in CPU scheduling. So even though they seem basic, linked list powers some of the most important computer functions. In today's video, we will tackle two essential linked list problems in Python. Before we dive into coding, here's what we will cover today. First, we will learn how to reverse a linked list, followed by detecting a cycle using fluid cycle detection algorithm. These concepts are frequently asked in technical interviews, so mastering them will give you an advantage in interviews. A linked list is a data structure where each node contains two parts, data and a reference to the next node. Unlike arrays, linked lists don't store elements in continuous memory, making insertions and deletions efficient. The three main types of linked list are singly linked list, doubly linked list, and circular linked list. Let's start with our first problem, reversing a linked list. Our goal is to change the direction of the links so that the last node becomes the first. We will use an iterative approach with 3 pointers: previous, current, and next. Now, let's look at the implementation. Here's the Python implementation. I will explain it line by line. First, we define a list node class to represent each node in the linked list. Each node stores a value and a pointer to the next node. Now, we define the function reverse linked list. We initialize previous as none, since the new tail will point to nothing, and current starts at the head of the list. Now we loop through the list. First we store the next node in next node. Then we reverse the next pointer to the current node to point to the previous. Finally, we move the previous and current forward by one step. Once we reach the end, previous will be the new head of the reverse list. So we return it. Since we only traverse the list once, the time complexity is order of n. And since we don't use extra space, the space complexity is order of 1, making this an efficient solution. Now let's move on to our second problem, detecting a cycle in a linked list. A cycle occurs when a node links back to a previous node, creating an infinite loop. We will use fluid cycle detection algorithm, also known as the two-pointer method. Let's go step by step through the implementation. We define a function has cycle. We initialize 2 pointers, slow moves 1 step at a time and fast moves 2 steps. Now we use a loop. If fast or fast dot next is none, the loop will stop, meaning no cycle exists. Otherwise, we move slow 1 step and fast 2 steps. If slow and fast meet at same point, it means there is a cycle and we return true. If the loop ends and the pointers never meet, we return false, meaning no cycle was found. Since we traverse list at most once, the time complexity is order of n, and since we only use 2 pointers, the space complexity is order of 1, making this an optimal approach. In today's video, we are going to learn, visualize and implement bubble sort in Python. We will cover how bubble sort works, a step-by-step visual example, Python implementation with detailed explanation. By the end of this video, you will understand how bubble sort works and when to use it. So let's get started. Bubble sort is a simple sorting algorithm that repeatedly compares adjacent elements and swaps them if they are in wrong order. It follows a step-by-step swapping process, pushing the largest element to their correct positions in each pass. While bubble sort is easy to understand, it is not the most efficient sorting algorithm for large datasets due to its complexity of order of n square in the worst case. This is the algorithm of bubble sort. First step is to compare adjacent elements, swap if they are in the wrong order, repeat the process for the entire array, largest element moves to the end in each pass, repeat until no swaps are needed. Let's take an example array 5, 3, 8, 4, 2 and sort it using bubble sort. This is the step-by-step sorting process. In the first pass, there will be 3 swaps and the array will be 3, 5, 4, 2, 8. In the second pass, there will be 2 swaps. 3, 4, 2, 5, 8 will be the output. In the third and fourth, 1 swap is present. And finally, it will be sorted and the result will be 2, 3, 4, 5 and 8. With each pass, the largest unsorted element moved to its correct position. Now, let's analyze the time complexity. Best case already sorted will be order of n. Worst and average case will be order of n square. Space complexity will be order of 1 if no extra memory is used. Bubble sort is great for learning but not efficient for large datasets because it requires multiple passes even for small lists. Now let's implement bubble sort in Python. Here's the Python code for bubble sort. Let's go through it step by step. In the first step, n equal to length of array. It will find the length of the array. In the second step, for I in range n, the outer loop runs n times to ensure full sorting. In the third step, swap equal to false, tracks whether any swaps happens. In the fourth step, for j in range n minus I minus 1, inner loop for adjacent comparisons. In step 5, if array of j greater than array of j plus 1, it swaps the elements if they are in the wrong order. In step 6, if not swapped, it is an optimization condition. It stops early if no swaps occurs. This makes the algorithm slightly faster when the list is already sorted. So this is the explanation which I gave for that code. A normal bubble sort always runs in order of n square, while an optimized bubble sort stops early if no swaps occurs, making it faster in some cases. For regular bubble sort, always run order of n square. Optimized bubble sort can run in order of n if the array is already sorted. In today's video, we will learn about selection sort, one of the fundamental sorting algorithms. We will cover its concepts, step-by-step working, implementation in Python, and a comparison with other sorting techniques. By the end of this video, you will be able to understand selection sort clearly and write your own Python code for it. Make sure to watch till the end. Before we dive into the implementation, let's first understand what selection sort is and how it works. Selection sort is a simple sorting algorithm that works by repeatedly finding the smallest element from the unsorted part and swapping it with the first unsorted element. It divides the list into two parts, the sorted part at the beginning, the unsorted part rest of the list. Always selects the smallest element from the remaining unsorted portion. Works in place, meaning it does not require extra memory. Time complexity is order of n square, not efficient for larger datasets. Now, let's break down selection sort step by step using a example array. So, example array is 53842. In the past one, we will find the smallest element in 53842 and the result will be 2. And it will swap with the first element, which is 5. 2 will come in place of 5. Array after pass 1 will be 2, 3, 8, 4 and 5. In pass 2, we will find the smallest element in 3, 8, 4 and 5. The smallest element is 3. No swap is required. Array after pass 2 will be 2, 3, 8, 4 and 5. In pass 3, we will find the smallest element in 8, 4 and 5. The smallest element in these 3 is 4. So we will swap it with 8. So array after pass 3 will be 2, 3, 4, 8 and 5. In pass 4, we will find the smallest element in 8 and 5. The smallest element is 5. So we will swap 5 with 8. And the result will be 2, 3, 4, 5 and 8. Then finally, the sorted array will be 2, 3, 4, 5 and 8. Notice that in every pass we pick the smallest number and move it to the correct position. Now let's analyze how efficient selection sort is. The time complexity. Best case is order of n square, worst case is order of n square, and average case is also order of n square. The space complexity is order of 1. It doesn't use extra memory. Why is selection sort inefficient? It always takes order of n square time even if the array is already sorted. It performs n square comparisons, making it slow for larger datasets. This is why selection sort is mainly used for small datasets or educational purposes. Now that we understand the logic, let's write the Python code for selection sort. This is the Python code for selection sort. So now let's go through the code line by line to understand how it works. In the first step, selection sort of array, we define a function selection sort that takes an array as an input. In the second step, for I in range n minus 1, we loop through the array considering I as the index of the first unsorted elements. In step 3, minimum index equal to I. We assume the first unsorted element is the smallest. In step 4, for j in range I plus 1 to n, we iterate through the rest of the array to find the smallest element. In step 5, if array of j greater than array of minimum index equal to j. If we find a smaller element, we update minimum index. In step 6, array of I, array of minimum of index equal to array of minimum of index, array of y. In this, we swap the smallest element found with the first unsorted element. Finally, the function returns the sorted array. Unlike bubble sort, selection sort performs fewer swaps. However, its time complexity remains order of n square, making it inefficient for larger datasets. So this is the step-by-step explanation I did in the previous slide. So go through it. So let's compare selection sort with other sorting techniques. This is the comparison between selection sort with bubble sort, insertion sort, merge sort, and quick sort. Selection sort is easy to implement but not the best choice for performance, that we can see from this table. In today's video, we will break down the insertion sort algorithm step by step. We will cover what insertion sort is, how the algorithm works, a Python implementation, dry run examples, time complexity analysis, and real-world applications. By the end of this video, you will be able to confidentially write and explain insertion sort yourself. Let's get started. Insertion sort is a simple sorting algorithm. It works the same way we sort playing cards in our hands. We start with the second element and compare it with the elements before it. If it's smaller, we shift the larger elements to the right and insert the current element in the correct position. This process repeats until the entire array is sorted. Let's break down the algorithm step by step. The first step, we start with the second element, treat the first element as already sorted. In the second step, we compare the current element with previous elements. We check if the current element is smaller than the elements in the sorted section. In the third step, we will shift the elements larger than the current elements one position to the right, which means we will move the elements that are larger than the current element one position to the right. In the fourth step, we will insert the current element at its correct position, which means we will place it in the correct position. In the fifth step, we will repeat for all elements. We will continue until all elements are sorted. Let's make this clearer with an example. Suppose we have the array 12, 11, 13, 5 and 6 as elements. In the past one, we will compare 11 and 12. Then we will insert 11 before 12. So the result will be 11, 12, 13, 5 and 6. In the past two, we will compare 13 with previous elements. There will be no change since 13 is larger than 11 and 12. In past 3, we will compare 5 with 13, 12 and 11. We will shift elements and place 5. So while comparing with 11, 12 and 13, 5 is smaller. So we will shift the element 5 to the first place. In the past 4, we will compare 6 with the previous elements and insert 6 in the second position, since 6 is smaller than 11, 12 and 13. Now that we understand the logic, let's implement this in Python. This is the Python code for insertion sort. Mainly, first we loop through the array starting from index 1. Then for each element, we compare it with the elements in the sorted section. After that, we shift the elements to make space. Then insert the current element in the correct position. Let's do a dry run of the code. Initial array is 12, 11, 13, 5 and 6. In the first iteration, we will compare 11 and 12. We will swap 11 and the result will be 11, 12, 13, 5 and 6. In the iteration 2, we will compare 13 with 11 and 12, and since 13 is larger than 11 and 12, no swap is needed. In the third iteration, we will compare 5 with 11, 12 and 13. Since 5 is smaller, we will shift the elements and place 5 in the first place. In the iteration 4, we will insert 6 in the second position, since while comparing 6 with the previous elements, 6 is smaller than 11, 12 and 13. This is how insertion sort works step by step. In the best case, it is order of n. In the worst case, it is order of n square. And also in average case, it is order of n square. And the space complexity is order of 1. For small or nearly sorted arrays, insertion sort is very fast. But for large random arrays, the quadratic time complexity makes it slower. These are some of the advantages and disadvantages of insertion sort. First one is simple to understand and implement, no extra memory required, and it is a stable sort, which means it maintains relative order of equal elements. Some of the disadvantages are it is inefficient for larger data sets, quadratic time complexity in the average and worst case, which means it have high time complexity for unsorted data. So when to use insertion sort? So it is best for small data sets and almost sorted arrays, and when stability is required. And it is not suitable for larger unsorted data sets and time sensitive applications with larger inputs. Some real world applications include online sorting, when elements array one by one, for example in the live leaderboards, small data tasks, sorting small arrays or linked lists, teaching and learning. It is great for learning how sorting algorithms works. In today's video, we will be discussing sorting algorithms, their efficiency, how they work, and their practical use cases. Sorting is one of the most fundamental operations in programming and choosing the right algorithm can significantly improve performance. By the end of this video, you will have a clear understanding of which sorting algorithm to use in different scenarios. So let's get started. Sorting algorithms are techniques that arrange elements in a particular order, like ascending or descending. They are fundamental in computer science and are used to organize data for easier access and manipulation. Choosing the right sorting algorithm is important because it can drastically affect the speed and resource usage of your programs. For example, a good sorting algorithm can turn an otherwise slow program into a lightning fast solution. Sorting algorithms are more than just theoretical concepts. They have real world impacts. Let's see why they are so crucial. Faster search and retrieval. Sorting data can be searched much faster, especially with algorithms like binary search. Data organization. Sorting makes it easier to handle larger datasets like organizing files in directories or arranging names in alphabetical order. Optimized algorithms. Many algorithms, like those in divide and conquer category, rely on sorted data to work effectively. Real world applications. Sorting is used in scheduling, prioritization, database indexing, and even graphics rendering. Sorting is everywhere, and knowing how different algorithms work gives you a big advantage as a developer. Sorting algorithms come in different flavors, and we can group them into three main categories. First one is simple sorting algorithm, second one is efficient sorting algorithm, and third one is specialized sorting algorithms. So in first one, simple sorting algorithms, we have bubble sort, selection sort, and insert sort. It is easy to understand but slow for larger datasets. In the second one, efficient sorting algorithms, we have merge sort, cube sort, and heap sort. It handles larger datasets better, but may use more memory or complex logic. In the third one, which is specialized sorting algorithms, we have counting sort, radix sort, and bucket sort. It doesn't compare elements directly and can be super fast for certain data types. Each category has its pros and cons, so understanding them helps you choose the right tool for your problem. Bubble sort, the basic sort. Bubble sort is the simplest sorting algorithm, but also the least efficient. So its concept is very simple. It repeatedly compares and swaps adjacent elements if they are in the wrong order. The time complexity is order of n square. It is very slow for larger datasets. Space complexity is order of 1. It sorts in place, so no extra memory is needed. It has stability and it preserves the relative order of equal elements. Best use case is for smaller datasets or teaching purposes. Its drawback is terrible for larger datasets because of its quadratic time complexity. In real life, you would almost never use bubble sort in production, but it's a great stepping stone to understand sorting concepts. The next one is selection sort. Selection sort improves on bubble sort a little, but still isn't very efficient. So its concept is it finds the smallest element and places it in the correct position, repeating this for each element. So its time complexity is order of n square, still quadratic. Space complexity is order of 1, sorts in place. It have no stability because it swaps elements without considering the order. So best use case is smaller arrays or situations with tight memory constraints. So its drawback is always order of n square even in the best case. Useful for small or fixed size datasets, but doesn't scale well for larger inputs. Next one is insertion sort. It works well for small or nearly sorted arrays. So it builds a sorted array one element at a time, inserting each element into its correct position. Its time complexity is order of n square, which is quadratic, but faster than bubble and selection sort in practice. Space complexity is order of 1, it sorts in place. It has stability, keeps the order of equal elements. Best use cases, small or nearly sorted arrays. Its drawback is slow for larger random datasets. Insertion sort is simple and can be very fast for almost sorted data, making it useful for small or dynamic datasets. Next one is merge sort, which is divide and conquer. Merge sort is a powerful algorithm that uses the divide and conquer approach. It splits the array, sorts the halves, and merges them back together. Its time complexity is order of n log n, very efficient for larger datasets. space complexity is order of n, needs extra space for the subarrays. It preserves the order of equal elements. Best use case is larger datasets or linked list. It have drawbacks like it requires extra memory, which might be an issue for huge datasets. Merge sort is reliable and has a predictable runtime, which makes it great for big complex sorting tasks. Next one is quicksort, which is the fastest in practice. Quicksort is one of the fastest and most commonly used sorting algorithms. It picks a pivot element, partitions the array, so smaller elements go to the left and larger elements to the right, and then recursively sorts the subarray. For the best and average time complexity, it is order of n log n, and for the worst, it is order of n square. The situation is if the pivot is poorly chosen. Space complexity is order of log n because of the recursion stack. It have no stability because elements can jump across position during partitioning. Best use cases, general purpose sorting works well for larger datasets. Its drawback is can degrade to order of n square in the worst case if the pivot is chosen poorly. Despite its worst case scenario, quicksort is very fast in practice and is even used in many programming libraries like Python sort function. Next one is heap sort. Heap sort is a comparison based algorithm that uses a heap data structure to sort elements. It builds a max heap, repeatedly extracts the maximum elements and places it in the correct position. Its time complexity is order of n log n for all cases. Space complexity is order of 1, sorts in place without extra memory. It have no stability because the heap structure doesn't guarantee the order of the equal elements. Its best use case is priority queues or when memory is tight. Its drawback is slower than quicksort in practice due to the heap operations. Heap sort is useful when space is a constraint, but quicksort is usually faster for general sorting tasks. Now we have counting sort and radix sort, which don't rely on element comparisons. First one is counting sort, counts the frequency of elements and uses the counts to build the sorted array. Its time complexity is order of n plus k, where k is the range of elements. Space complexity is order of k for the count array. It's best for smaller integer ranges. And its drawback is inefficient for larger ranges or floating point numbers. In radix sort, it sorts the elements digit by digit from the least significant to the most significant. Its time complexity is order of nk, where k is the number of digits. Space complexity is order of n plus k. It is best for fixed length numeric data like phone numbers or zip codes. Its drawback is it's not ideal for floating point numbers or negative values without modifications. These algorithms are blazing fast for specific scenarios but aren't as flexible as comparison-based sorts. Let's break down the time and space complexity of all the algorithms we have discussed so far. For the bubble sort, the best case is order of n, average case is order of n square, and worst case is also order of n square. For selection sort, the best case is order of n square, average case is order of n square, and worst case is also order of n square. In insertion sort, best case is order of n, average case is order of n square, and worst case is also order of n square. For merge sort, best case is order of n log n, average case is order of n log n, and worst case is also order of n log n. For quicksort, best case is order of n log n, and average case is also order of n log n, but the worst case is order of n square. For heap sort, best case is order of n log n, average case is order of n log n, and worst case is also order of n log n. From this table, you can see why algorithms like merge sort and quicksorts are widely used and why counting sort and radix sort are valuable for certain kinds of data. Choosing the right algorithm depends on your specific problem. Let's break it down. For smaller datasets, insertion sort or bubble sorts are simple and fast. For larger datasets, merge sort or quicksort handles big arrays efficiently. For almost sorted data, insertion sort can sort with minimal comparisons. For smaller integers or fixed range, counting sort or Reddick sort are lightning fast. When memory is tight, heap sorts work without extra space. Understanding these trade-offs help you make the best choice for your project. Some real-world scenarios or use cases includes quicksorts and merge sort for databases, indexing, and file system. And for search engines, Reddick sort and counting sort are used. The heap sort is used for priority queues and job scheduling. And for graphic applications and animation tools, we use bucket sorts or Reddick sort. Knowing which algorithm to apply in different scenario is a powerful skill for real-world development. In today's video, we are diving into the linear search algorithm. This is one of the simplest and most fundamental algorithms in computer science, but understanding it deeply will help you build a solid foundation for more complex algorithms. We will break down step by step, covering how linear search works, its implementation, time complexity, and real-world applications. So let's get started. What is linear search? Linear search is a simple searching algorithm where we check each element in a list one by one until we find the target element or reach the end of the list. It's called linear because the number of comparisons grows linearly with the size of the list. So the key points to remember are: first, we start at the first element of the array, then we compare each element one by one with the target value, and if we found a match, we will return the index of that element. Otherwise, if no match is found, by the end of the array, we will return -1. For example, imagine you have a list of numbers 15, 23, 7, 42, 89, and 31, and you want to find the number 42. With linear search, you will start from the first element, check each one, and eventually find 42 at the index 3. Let's understand the key characteristics of linear search. It works on both sorted and unsorted data. Means you don't need to sort the data beforehand. You can search directly. Second point, can be implemented on arrays, list, and linked list. Linear search works on almost any linear data structure. Third point is best suited for small data sets. It means for small lists, the simplicity of linear search makes it a great choice. Next point is does not require pre-processing, which means unlike binary search, linear search doesn't need any preparation. The last point to remember is it is simple and easy to understand. Means the logic is straightforward, making it perfect for beginners. Now let's talk about the time complexity of linear search, which tells us how the algorithm performs as the input size grows. The best case is order of 1 if the target element is at the first position. We find it in one step. The worst case is order of n if the element is at the last position or not in the list at all. We have to search the entire array. The average case is order of n. On average, linear search will check half of the elements before finding the target. The space complexity is order of n. Linear search uses constant space because it only requires a few variables for iteration, regardless of the array size. Now, let's break down the algorithm step by step. First, we begin the search process. Then, we will input the array and target element. Then, we loop through each element of the array and we compare the current element with the target. That is the fourth step. If array of I equal to key. In this step, we will check if the current element matches the target. And in the fifth step, if a match is found, we will return the index. Next, if no match is found, we will return -1. Then we complete the search. Here is a clean pseudocode representation of the linear search algorithm. The loop starts at the index 0 and goes up to the last index. It compares each element with the target key. If it finds a match, it returns the index of the element. If no match is found, after checking all the elements, it returns -1. Let's see the Python code for linear search in action. So this is the Python implementation of the linear search. So we will define the function linear search. We will pass the array and key. Then for I in range length of array, if array of I equal to key, we will found the element, we will return the I, which is the index of the element. And after completing the loop, if the element is not found, we will return -1. That's how we can implement the linear search in Python. Let's trace the algorithm step by step with an example. For example, we need to check 42 in the list 15, 23, 7, 42, 89, and 31. So in the first step, we will be at index 0 and the element is 50. Since it doesn't match with 42, we will go to the next iteration. In step 2, the index is 1 and the element is 23, as you can see. And 23 is not matched with 42, and we will go to the next iteration. In the third step, the index is 2 and the element is 7. Since it doesn't match with 42, we will go to the next iteration. So in the fourth step, the index is 3 and the element is 42. Since 42 is matched with 42, we will return the index 3, since 42 is present at the index 3. Linear search is useful in many situations. Searching in smaller datasets when data is unsorted, searching in data structures like linked list when elements are frequently added or removed. So these are the some of the use cases of linear search. So here are some practical examples of linear search. To find a contact in an unordered phone book, to look for an item in a grocery list, searching for a student in an attendance register, finding a specific file in an unorganized folder. Some of the advantages and disadvantages are, so the advantages include easy to implement, there is no complex logic needed, works on all types of lists, sorted or unsorted list. It doesn't matter, it works on all types of list. No additional memory is required. So some of the disadvantages are slow for larger dataset, it is inefficient for long list, not optimal compared to other search algorithms. So some alternative includes, for sorted data, we can use binary search, which is order of log n, is much faster than linear search. So this is the performance comparisons with linear search, binary search, and jump search. So for linear search, the best case is order of 1, worst case is order of n, and average case is order of n. It works on sorted as well as unsorted data. So next, binary search, it best case is order of 1, worst case is order of log n, average case is order of log n. It works only on sorted data and it doesn't work on unsorted data. Next is jump search. Its best case is order of 1, worst case is order of root n, and average case is also order of root n. It works only on sorted data and doesn't work on unsorted data. In today's video, we are diving into a fundamental searching algorithm, binary search. We will break it down step by step, covering how it works, writing Python code, understanding its complexity, and exploring real-world use cases. By the end of this video, you will not only understand binary search, but also know when and why to use it in your projects. So let's get started. So what is binary search? Binary search is an efficient algorithm used to find an element in a sorted array. It works by repeatedly dividing the array into halves. So unlike linear search, which scans elements one by one, binary search follows a divide and conquer approach. So here's the idea. Take the middle element of the array. If it matches the target, you are done. That's it. You found the target element. If the target is smaller, search only the left half. If the target is larger, search only the right half. This way, with each step, you cut the search space in half, making the algorithm incredibly fast compared to a linear search. How binary search works? Let's walk through the steps of binary search. First, it starts with a sorted array, then find the middle element equal to left plus right divided by 2. Then we will compare the middle element with the target. If it matches, the element is found. If it's smaller, we will search the right half. If it's larger, we will search the left half. We will repeat this process until the element is found or the search space becomes empty. By cutting the array in half with each step, binary search achieves amazing speed, especially for larger datasets. So binary search is powerful, but it comes with a few requirements. First one is sorted array. The data must be sorted, otherwise binary search won't work. Second one is random access structure. It works best with arrays or lists where elements can be accessed directly by index. Third one is finite elements. The array should have a defined length, so you can calculate the middle indices. If these conditions are met, you are ready to use binary search effectively. Let's break down the complexity of binary search. For best case, it is order of 1 if the elements is right at the middle. So elements found in the first comparison. Worst and average case is order of log n. For the worst case, the array size halves at each step. For the average case, typical search time. So and for space, iterative version will be order of 1, which is constant space, and for recursive version, order of log n due to the call stack. This makes binary search incredibly fast and memory efficient for larger data sets. This is the pseudocode for binary search algorithm. First, we define the function binary search. We will pass array and target value, left equal to 0, right equal to length of array minus 1 till the end. While left less than or equal to right, we will find the middle as left plus right divided by 2. If array of middle equal to target, we will return mid since the target is found. Else if array of mid less than target, we need to search the right half, which is left equal to mid plus 1. So then it will search from left to right. Then if in the else part, if we have to search the left half, so right equal to mid minus 1. Finally, after iterating to the array, if the element is not found, we will return minus 1. So this is the Python implementation of binary search. So first we will define the function, then we will pass array and target, and left comma right equal to 0 comma length of array minus 1. So we will assign left with the index 0 and right with the last index. While left less than or equal to right, we will find the middle element, which is mid equal to left plus right divided by 2. If array of mid equal to target, we will return mid, which is the target element. If array of mid less than target, we will update the left by mid plus 1. In the else case, we will update the right by mid minus 1. Finally, if the element is not found, we need to return minus 1. So let's dry run an example to visualize binary search in action. So for example, let the array be 10, 20, 30, 14 and 50 and the target be 30. In the first step, the left will be 0 and the right will be 4 and middle will be 0 plus 4 divided by 2, which is 2. And we will find the array of mid as 30. Since the target is 30, it will match the array of mid and we will return target as 30. So in this case, binary search finds the element in just one step. So where is binary search useful? Finding elements in sorted arrays, database indexing and lookups, dictionary or phone book searches, then price range filtering in e-commerce, debugging tools such as Git bisects. So why use binary search? It is used in searching in sorted arrays or lists, finding elements in dictionaries or phone books, database search optimizations, debugging, and game development. For example, collision detection or pathfinding. Some of the advantages includes fast and efficient. It have order of log n complexity. It is memory efficient, low space complexity, works well with larger datasets, simple to implement, and predictable performance. So some of the disadvantages include it requires sorted data, not ideal for small or unsorted datasets, limited to random access data structures. Recursive approaches uses extra space, harder to implement in linked list due to no direct indexing. In today's video, we will learn about recursion. Whether you are preparing for coding interviews or learning data structures, recursion is a must-know topic. So let's break it down step by step. I will explain how recursion works, where it's useful, and even walk you through some Python code examples. Let's get started. So what exactly is recursion? Recursion is a technique where a function calls itself to solve smaller instances of a problem. It's like solving a big problem by breaking it down into a smaller, similar subproblems. The function keeps calling itself until it reaches a base case, a condition where the recursion stops. For example, calculating the factorial of a number is a classic recursive problem. Factorial of n equal to n into factorial of n minus 1. We solve the larger problem by solving smaller versions of the same problem. It's like looking into a mirror that reflects another mirror. The pattern repeats itself. Let's now understand how recursion actually works. A recursive function has two main parts. First one is base case and the second one is recursive case. In the base case, this stops the recursion and prevents infinite loops. In the second case, recursive case, this breaks the problem into smaller chunks and makes a recursive code. Imagine recursion like a series of doors. Each recursive call opens a new door and you can close the doors until you reach the end of the hallway. The base case. Once you hit the base case, you close the doors one by one, returning the results back through each function call. So the steps in recursion are: we will call the function with an initial input, we will divide the problem into smaller subproblems, solve the subproblems recursively, combine the results if needed. Let's walk through an example to see recursion in action. We will calculate the factorial of 3. So in the first step, factorial of 3 equal to 3 into factorial of 2. So factorial of 2 we need to calculate. It will be 2 into factorial of 1. So factorial of 1 equal to 1, which is the base case in finding the factorial. So now we return the results back, which is 3 into 2 into 1, which is equal to 6. This back and forth flow happens through the call stack, where each function call waits for the next one to finish and then returns the result. Here's a general structure of a recursive function in Python. So first we will define the recursive function. We will pass the parameters. If base condition, we will return the base case value, else result equal to recursive function of smaller problem. We are making it into smaller chunks. We will return the process result of result. Let's implement factorial in Python. This is the factorial calculation implementation in Python. So we will define the factorial of n. If the n equal to 1, we will return 1, which is the base case, and 1 is the base case value. In the else case, we will return n into factorial of n minus 1. If you call factorial of 5, the function will recursively calculate 5 into 4 into 3 into 2 into 1, which results in the 120. Now, let's talk about the efficiency of recursion. Time complexity is order of n for linear recursion like factorial or Fibonacci, order of 2 raised to n for exponential recursion like naive Fibonacci. Space complexity is order of n due to the recursive call stack. Can be reduced with optimization like tail recursion or memoization. Recursion comes in many forms. Let's break them down. Direct recursion. Function calls itself directly. Indirect recursion. A function calls another function which in turn calls the original function. Tail recursion. The recursive call is the last operation in the function. Head recursion. The recursive calls happen before other operations. Tree recursion. A function makes multiple recursive calls. For example, Fibonacci. Each type has its pros and cons, but understanding them helps you decide the best approach for different problems. So recursion is super useful in a variety of real-world problems. Mathematical computations like finding the factorials, Fibonacci series, GCD, and etc. In trees and graphs algorithms like traversals and depth first search. In divide and conquer algorithms such as merge sort and quicksort. Dynamic programming, solving sub-problems recursively. For string manipulation to find the palindrome checks for string reversals. Whenever a problem has a smaller, repeatable substructure, recursion is usually a great choice. Let's quickly go over with the advantages of recursion. Simpler code. Recursive solutions are often shorter and more intuitive. Solves complex problems easily. Ideal for problems with repetitive substructures like trees. Natural fit for divide and conquer. Recursion aligns perfectly with algorithms that split problems into smaller pieces. But recursion isn't perfect. It has some disadvantages also. So memory overhead, performance issue, difficulty to debug are some of the disadvantages recursion have. So memory overhead means recursive calls consume stack space, which may lead to stack overflow. Performance issues, recursion can be slower and less efficient than iteration for certain problems. Difficulty to debug, tracking recursive calls and understanding stack frames can be tricky. Recursion isn't just theoretical, It's used in real-world applications like web crawling, visiting links on a web page recursively, file system for navigating through folders and subfolders, data parsing, parsing nested structures like JSON or XML, AI and games, solving mazes, game state trees and puzzles like Sudoku. In today's video, we are diving deep into classic recursion problems. We will explore what recursion is, break down some common recursive problems, and go through the Python code step by step. By the end of this video, you will be confident enough to tackle recursion-based coding problems easily. Let's start with the basics. What are recursive problems? These are problems that can be solved by breaking them down into smaller identical subproblems. We solve the smaller instances, then combine the results to solve the main problem. In recursion, a function calls itself, but to avoid infinite loops, we need a base case, a condition where the recursion stops. Why use recursion? It simplifies complex problems, especially those involving trees, graphs, or nested structures. However, recursion can sometimes lead to high space complexity, so we need to be mindful of that. Let's start with a simple yet classic recursive problem, factorial of a number. The factorial of a number n is the product of all positive integers from 1 to n. The recursive formula is n factorial equal to n into n minus 1 factorial. The base case is factorial of 1 equal to 1. So for example, if the factorial of 5, we need to print the output 120 as 5 into 4 into 3 into 2 into 1 equal to 120. Time complexity is order of n and space complexity is order of n. So let's break down the code. So first we define a function called factorial that takes one parameter n. This is the base case. If n is 1, we return 1 and stop the recursion. If n is not 1, we move the recursive case. We will return n into factorial of n minus 1. We multiply n by the result of factorial of n minus 1. This keeps breaking the problems into smaller subproblems until we hit the base case. So for example, factorial of 5 is 5 into 4 into 3 into 2 into 1, which result in 120. Next, we have the Fibonacci sequence. It's a series where each number is the sum of the two preceding ones. The recursive formula is f of n equal to f of n minus 1 plus f of n minus 2. The base case is f of 0 equal to 0 and f of 1 equal to 1. For example, for f of 5, we need to print 5 elements, 0, 1, 1, 2, 3 and 5. Time complexity is order of 2 raised to n and space complexity is order of n. So here's the code for Fibonacci sequence. So first we define a function named Fibonacci with one parameter n. So base case is like if n is 0 or 1, we return n. So this is the base case. If n less than or equal to 1, we will return n. In the else case, for larger values, we compute the sum of the previous two numbers. Then we return n minus 1 plus n minus 2. This is the recursive call, breaking the problem into smaller subproblems. Next comes the Tower of Hanoi problem. It is a famous recursive puzzle. The goal is to move n disk from a source node to a target node using an auxiliary node. The rules are only one disk can be moved at a time. A disk can only be placed on a larger disk or an empty node. For example, if n equal to 3, there are 7 moves. Time complexity is order of 2 raised to n and space complexity is order of n. So let's see the recursive solution. First, we define the function with n disk and 3 routes. If n equal to 1, base case, if there is only one disk, move it directly. Then we will move the top n minus 1 disk to the auxiliary route. Then we will print the move for the nth disk. Then move the n minus 1 disk from the auxiliary route to the target route. Next is the binary search. It searches for an element in an sorted array. It repeatedly divides the array in half. For example, if the array is 1, 3, 5, 7 and 9 and we need to find the target 7, the result should be 3 since 7 is present at the index 3. Time complexity is order of log n. Space complexity is also order of log n. This is the code for binary search. First we define the binary search. We will pass array, the low, the high, and the target. If low greater than high, we will return -1, which is the base case. Then we will find the mid as low plus high divided by 2. If array of mid equal to target, we will return the middle value. If array of mid greater than target, we will return the binary search and array low, mid -1, and target. In the else case, we will return mid plus 1, high, and target. This is for the left case and this is for the right case. Next, we have the string reversal. It is to reverse a given string. The approach is simple. We swap the first and last characters, then recurse on the remaining substring. For example, if the input is HELLO, we need to get the output OLLEH. Time complexity is order of n. Space complexity is also order of n. So this is the code for it. First, we define the reverse string. We will pass the string. If the length is 0, we will return s, which is the base case. In the else case, we return s of -1 plus the reverse string, the last element in it. Next, we have the permutations of a string. It generates all possible permutations of a string. For example, permutations of ABC is ABC, ACB, BAC, BCA, CAB, and CBA. Time complexity is order of n factorial and space complexity is order of n. This is the code for permutation. So first, if step equal to length, we will join the string. Then for I in range step to length of s, we will copy it. S of copy equal to character for character in s. S of copy of step comma s of copy of I equal to s of copy of I comma s of copy of step. We will recursively call the permutation function. Next is tree traversal. It traverses a binary tree recursively in order, pre-order, or post-order. So for example, tree with nodes 1, 2, 3, the in order is 2, 1, 3. Time complexity is order of n and space complexity is also order of n. This is the Python code for it. In order traversal, we will pass the root. If root, in order traversal of root dot left, and print root dot data, in order traversal root dot right. So this is the code for in order traversal. In today's video, we are going to discuss about backtracking with recursion. This technique helps us solve complex problems by exploring all possible solutions and backtracking when a decision leads to an invalid state. We will break this down step by step with examples, advantages, and limitations, and we will discuss how backtracking works in Python. Let's get started. So let's start with the basics. Backtracking is a problem-solving technique that involves building a solution incrementally. If at any point we find that the current partial solution is invalid or won't lead to the correct answer, we backtrack by undoing the last step and trying a different path. Think of it like navigating a maze. You choose a path, but if you hit a dead end, you back up to the last decision point and try another route. This approach works great for problems involving decision making like puzzles, combinations, and permutations. Imagine trying to arrange books on a shelf and each position can hold only certain types of books. You try placing one, but if it doesn't fit, you take it out and try another one. That's backtracking. Backtracking relies on 4 key concepts. First one is recursive exploration. We use recursion to explore all possible solutions. Second one is base case, the stopping condition that tells us when we have reached a valid solution or exhaust all possibilities. Third one is constraint checking. We check if the current choice is valid. If it violates the problem's constraints, we discard it. The fourth one is backtrack step. If a choice doesn't lead to a solution, we undo it and try another option. For example, in the nqueues problem, we place a queue on the board, check if it's safe. If not, we remove the queue and try another position. That's backtracking in action. Let's look at a simple example to understand backtracking better. Finding all subsequence of a string. A subsequence is a sequence derived from another sequence by deleting some elements without changing the order. For example, subsequence of A, B, C are A, B, AB, AC, and so on. So this is the code for finding all subsequence of a string. So let's break the code step by step. First, we will find the subsequence. It will take string, current index, and current subsequence as parameters. Then we have the base case. If index reach the end of the string, which is if index equal to length of the string. If index reaches the end of the string, we print the current subsequence and return. Then recursive inclusion. Here in the first recursive call, we add the current character to the subsequence and move to the next index. Next, in the second call, we exclude the current character and explore the next index. This recursive inclusion and exclusion generate all possible subsequences. So for the input ABC, the output will be ABC, AB, AC, A, BC, B, C, and an empty string. These are some of the real world problems solved with backtracking. First one is the n-queue problem. The n-queue problem requires placing n queues on a n by n chessboard such that no two queues attack each other. Queues attack in the same row, column, and diagonals. The approach is simple. We use backtracking to explore all possible placements, then place queue row by row, ensuring the current placement doesn't conflict with previously placed queues. If a valid placement is found for all n queues, store the configuration. If a conflict arises, backtrack by removing the last placed queue and trying the next possibility. The next one is the Sudoku solver. Given a partially filled 9 by 9 Sudoku grid, fill in the missing numbers following these rules. Each row must contain the digits 1 to 9 exactly once. Each 3 by 3 subgrid must contain the digits 1 to 9 exactly once. To solve this Sudoku solver, the approach is simple. By using backtracking to fill in the empty cells, then we'll try placing numbers 1 to 9 in an empty cell. Then we check if the placement is valid based on the constraints. Then if valid, move to the next empty cell. And if a conflict occurs, backtrack by removing the last placed numbers and trying the next option. We will stop when the grid is completely filled. Next is the string permutation. Given a string, generate all possible orderings of its characters. And the next one is rat in a maze. And a rat is placed in the top left corner of a maze and needs to reach the bottom right corner. The maze consists of open paths 1 and walls indicated as 0. The rat can move left, right, up, or down. The approach is simple. We use backtracking as the previous 3 problems to explore all possible paths, move in each possible direction, and if a dead end is reached, backtrack and try a different path and mark visited cells to avoid cycles. So these are some of the classic backtracking problems which are commonly used. Backtracking can be powerful but computationally expensive. So time complexity varies based on the problem, usually order of 2 raised to n for subsets or order of n factorial for permutations. Space complexity is order of n due to recursive stack space. Optimization tip is like use pruning to avoid exploring unnecessary branches. For example, using a Boolean array to track visited elements. Some of the advantages include simple and elegant. It breaks problem into smaller, manageable subproblems. Systematic exploration, it checks all possible solutions. No need for complex data structures. Then it is versatile and brute force alternative. Some of the disadvantages of backtracking include its exponential time complexity, can be very slow for larger inputs, high space usage, recursion uses stack space, then redundant computation. It might explore the same subproblems repeatedly, that not always feasible, and it is difficult to debug since recursive logic can be tricky to trace. So when exactly to use backtracking? When brute force is too slow, we can use backtracking. When there are multiple possible solutions, we can use backtracking. When constraints need to be checked dynamically, we can use backtracking. Some example use cases are for solving puzzles like crossword, Sudoku, etc., generating combinations and permutations, pathfinding problem in AI and robotics. So some real-world examples include web crawling, file system, data parsing, AI and games, solving mazes, game state trees, and puzzles like Sudoku. In today's video, we are diving into one of the most important concepts in data structure, hashing and hash maps. We will break it down how hashing works, what hash maps are, their advantages, disadvantages, and even real-world applications. Let's get started. Let's start with the basics. Hashing is a technique where data is mapped to a unique fixed size value called a hash code. This is done using a special function called a hash function. Imagine you want to store student records based on their ID. Instead of searching through every record, a hash function turns the ID into an index, and you can directly access that index in the array, making lookup super fast, typically in constant time or order of n complexity. A hash function is the engine of hashing. It takes an input like a string or number and generates a unique number, the hash code. A good hash function has a few key properties. First one is deterministic. The same input always produces the same output. Second one is efficient. It computes hash value effectively. Third one is uniform distribution. It spreads elements evenly across the table to avoid clustering. The fourth one is low collision rate, which means it reduces the chances that two inputs produce the same hash value, which would cause a collision. A hash table is a data structure that stores key value pairs. A hash map is a more abstract version of this, where each key is hashed to find the index for its value. For example, in Python, dictionaries are implemented as hash maps. You can store and access values by their unique keys in constant time, thanks to the underlying hash table structure. Here's a step-by-step breakdown of how hashing works. Key input. You provide a key like the word apple. Hash function. The hash function converts the key into a hash value like 4. Array indexing. The hash value becomes the index in the array. Storage. The key value pair is stored at the index. Retrieval. When you search for the key, the hash function computes the same index, giving you direct access to the value in constant time. Let's look at a simple hash map implementation in Python. The first step is initialization. We create a hash table with a fixed size. The second step is hash function. Computes the index from the key. Third step is insertion. Adds a key value pair to the correct index. And the last retrieves a value by computing the index from the key. This implementation uses chaining to handle collisions. Multiple key value pairs can exist at the same index in a list. Collision happens when two keys generate the same hash value. We solve this in two ways. First one is chaining, stores multiple pairs at the same index in a linked list. Second one is open addressing. It searches for the next available slot. In the best case, it is order of 1, which is direct lookup. And in the worst case, with collision, it is order of n. So the time complexity is order of 1 for the best case and order of n for the worst case. The space complexity is order of n. It depends on the number of elements. Hash maps are incredibly fast, but they are not perfect. So some of the advantages are it have fast lookups and insertions, easy to use key value pairs, and no need for sorted data. Disadvantages includes collisions can slow performance, memory overhead from unused slots, and hash function complexity affects speed of the program. These are some of the real-world applications of hash maps. Databases. Indexing for fast lookups. Caching. Stores frequently accessed data. Symbol tables. Compilers use hash maps to track variables. Networking. Routing tables in networking devices. In today's video, we are going to discuss about hash map problems in Python. Today, we will break down two essential Python problems, counting frequency and finding duplicates in a list using hash maps. I will explain the concepts, walk you through Python code step by step, and discuss real-world applications. So let's get started. Before we dive into the problems, let's understand what a hash map is. A hash map is a data structure that stores data in key value pairs. In Python, hash maps are implemented using dictionaries. They provide constant time complexity for insertions, deletions, and lookups, making them extremely efficient. Hash maps are widely used in coding interviews and real world applications, so mastering them is a valuable skill. Let's tackle the first problem, which is counting frequency. So we want to count how many times each element appear in a list. For example, if the input is like 1 2 2 3 3 3, and then the output should be 1 is 1, which is 1 is repeating 1 times, 2 is 2, which is 2 is repeating 2 times, 3 is 3, which is 3 is repeating 3 times. This is the Python code implementation for counting the frequency. We start by defining a function, count frequencies, that takes a list called nums. We initialize an empty dictionary frequency of map to store elements as keys and their counts as values. We loop through each element in the list using a for loop. The get method checks if the element already exists in the dictionary. If not, it returns 0 as the default value. We increment the count of each element by 1. Finally, we return the frequency of map containing the frequency of each element, and the output of this will be 1 1, 2 2, and 3 3, as explained in the previous slide. Next, let's solve the finding duplicates problem. It is to identify the elements that appear more than once in a list. For example, if the input is 4 5 6 4 7 5, here we can see 4 is repeating 2 times and 5 is also repeating 2 times. So 4 is present 2 times in this list and 5 is also present 2 times in the list. So our aim is to identify the elements that appear more than once in a list. So if the input is like this, then we need to print 4 and 5 since it is appearing 2 times. This is the code implementation of finding the duplicates. First, we define a function find duplicates that takes a list nums. Then we will create an empty dictionary frequency map to store frequencies. Then we use a set called duplicates to collect elements that appear more than once by avoiding repeated entries. We will loop through the list, updating the count of each element. Then if an element's counts exceed 1, add it to the duplicate list. Then we will convert the set to a list and return it. And for this input, the output will be list containing elements 4 and 5. Now let's discuss real world applications of these techniques. Text analysis. It's count word occurrences in documents or articles. Then finding repeated elements in datasets. Caching results to optimize algorithms. Understanding these use cases helps you see how these small problems build up to solve larger complex scenarios. Now, let's break down the time and space complexity. For counting frequency, it is order of n. We traverse the list once. For finding duplicates, it is order of n. Again, a single pass through the list. Space complexity is order of n. We use extra space to store the hash map, and in the case of duplicates, a set. These optimal complexities make hash maps a go-to solution for many coding problems. In today's video, we are going to discuss about hash map problems in Python, part 2, where we will dive into solving two more essential problems, the two-sum problem and finding the first non-repeating character. By the end of this video, you will have a solid grasp of how to leverage hash maps for efficient problem solving. So let's get started. In part 1, we explored counting frequencies and finding duplicates using hash maps. In this video, we will tackle two new problems that are frequently asked in coding interviews. The two-sum problem, which is to find two numbers in an array that add up to a target. Then the first non-repeating character, find the first character in a string that doesn't repeat. So understanding these problems will strengthen your coding skills and improve your chances of acing technical interviews. So basically, we have explained what hash maps in the previous video, so check that. So for an overview, a hash map is a data structure that maps keys to values. So let's break down the first problem, two-sum problem. Given an array of integers and a target sum, return the indices of two numbers that add up to the target. For example, if the input is a list containing 2, 7, 11, 15 and the target is 9, we need to output 0 and 1, which is the indices of 2 and 7. So 2 plus 7 equal to 9. So we will get the target 9 by adding these two elements in this list, and the indices of it is 0 and 1. So we need to output 0 and 1. So this is the Python implementation of two-sum problem. We will break this down step by step. First, we initialize a hash map. This stores element as keys and their indices as values. Then we iterate through array. For each element, we calculate its complement, which is target minus current element. Then we check the hash map. If the complement already exists in the hash map, we will return the indices. Otherwise, store the element. Then we will add the element and its indices to the hash map. This approach ensures we only traverse the array once, making the solution highly efficient. So where we can use this solution in real life? Some use cases include financial apps or financial calculations, finding two expenses that match a budget. In gaming, pairing items to achieve a desirable power-up value. In logistics, matching inventory items to fill an order. So complexity is like, for time complexity, it is order of n, linear time due to single array traversal. Then space complexity is also order of n due to its extra space for the hash map. Next up, let's solve the first non-repeating character problem. It is to find the first character in a string that doesn't repeat. For example, if the input is lead code, here L is the first character that only appear once. So this problem is to find the first character in a string that doesn't repeat. This is the Python code implementation for first non-repeating character. So this code counts the frequency of each character and returns the first with a count of 1. So let me explain it step by step. First, we will count the character frequencies. Use a hash map to count each character occurrences. Then we scan the string again. We will check each character's count in the hash map. Then we will return the first unique character. The first character with a count of 1 is the answer. Then we will return none if no unique character exists. This approach is both intuitive and efficient. So where can this solution be useful? In text analysis, finding distinct words or letters in a document. In data streaming, we are detecting the first non-repeating event in a log. Natural language processing for identifying distinct element in a sequence. Its time complexity is order of n and space complexity is also order of n. It's been an amazing journey, and today we will wrap things up by discussing essential tips for solving DSA problems, practice strategies, and resources to guide your future learning. This session will help you stay on track and continue growing as a programmer. So let's dive right in. Throughout the series, we explore fundamental data structures like arrays, stacks, queues, and linked lists. We work through searching and sorting algorithms, learned recursion, and tackled real coding problems. But learning DSA doesn't end with understanding concepts. Practice is where the real mastery happens. You might know an algorithm in theory, but solving problems regularly sharpens your intuition. It improves your coding speed and helps you develop a problem-solving mindset. The more you practice, the better you will get at spotting patterns and choosing the most efficient approach. When approaching a problem, take time to carefully understand the statement. Misreading a requirement can lead to wasted effort. Break the problem into smaller chunks. Use pen and paper to visualize your approach and write pseudocode to structure your thoughts. Testing your solution with multiple edge cases ensures it's robust and ready for real-world use. Start with simpler problems to build confidence and then progressively tackle more complex ones. You should recognize patterns. Many problems are just variations of common techniques like two-pointers, sliding window, or dynamic programming. Pay attention to time and space complexity and always try to optimize your solution. And if you get stuck, don't worry. Review explanations and learn from your mistakes. Online platforms like LeetCode, HackerRank, and Geeks for Geeks are good for practice. They offer thousands of problems across difficulty levels, and the discussion sections often provide valuable insights. Make it a habit to solve at least one problem a day to build momentum. If you want to dive deeper, books like Cracking the Coding Interview provide structured guidance. Online courses and YouTube tutorials can help you grasp complex concepts visually. Joining live coding sessions or participating in coding competitions can also supercharge your learning. You can also check our DSA in Python playlist. Applying DSA concept in real-world projects make your learning more tangible. Build small projects that involves sorting, searching, or data manipulation. Try implementing well-known algorithms from scratch or create tools that solve practical problems. This reinforces your understanding and strengthens your portfolio. Mastering DSA is a continuous journey. Stay consistent, stay curious, and never be afraid of failure. Every problem you solve makes you a better programmer. Join coding communities, participate in hackathons, and keep pushing your limits. And most importantly, enjoy the process because every line of code brings you one step closer to your goals. Thank you for being part of this series and happy coding.